Welcome to AI Paper Slop. We are getting straight to it today. The paper is called AutoLab. Can frontier models solve long-horizon auto research and engineering tasks? And honestly, here is the absolute core of what you need to know right out of the gate.
Yeah, there's a lot to unpack.
For sure. So first, the benchmarks we currently use to evaluate AI agents, they're basically lying to us. They test single-turn coding. But real engineering is, it's an iterative, long-horizon grind. AutoLab fixes this with this massive 36-task benchmark.
Right. Second
big thing, the ultimate indicator of a model's success isn't its initial zero-shot brilliance, it's sheer persistence. Third, Claude Opus 4.6 just completely destroyed everything on this leaderboard with a score of 0.68, while heavyweights like GPT 5.4 actually failed because they quit too early.
We just clock out.
Exactly. And finally, the agent framework, like the actual software harness, wrapping the model matters almost as much as the model itself. In fact, wrapping a cheap, small model in a really aggressive, iterative harness can make a 7-cent API call outperform a massive frontier model.
Which is just wild for the economics of this stuff.
It totally changes the math. So let's unpack the mechanics here. Why have standard benchmarks been giving us this false sense of security about AI software engineering?
Well, the central issue is really that we've been evaluating these models in a complete vacuum. The standard approach up to this point has basically been to give a model a prompt, wait for it to spit out a standalone Python script, and then just run a quick unit test to see if it compiles.
Right.
And if it passes, boom, we score it highly and call it state-of-the-art.
Yeah, but that's treating software engineering like a multiple choice exam. You have a discrete question, you provide a discrete answer, and you move on. But for those of you listening who actually work in ML engineering or systems architecture, that is never how it works.
Never.
You're usually dropped into this massive, messy code base with 50 undocumented dependencies, and your boss tells you to make a specific module 10 times faster.
Oh, absolutely.
You try an approach, the server crashes, you have to read the stack trace, and you just iterate. It's a multi-day hackathon where your first 10 ideas are just garbage.
Exactly. And that exact feedback loop is the core mechanism that AutoLab is actually designed to evaluate. Okay. The researchers constructed this benchmark to be ultra-long horizon. It consists of 36 tasks completely curated by human experts, and these aren't simple leet code exercises.
No, they're brutal.
They really are. They're spread across 4 very intense domains. So you have 15 system optimization tasks, 10 puzzle and challenge tasks, which involve complex algorithmic reductions and resource scheduling.
Right.
Then there are 7 model development tasks, which actually require the agent to do things like pre-train a small transformer or fine-tune an OCR model from scratch.
Wow.
Yeah. Finally, 4 brutal CUDA kernel optimization tasks.
Okay, I want to pause on the setup here because there's this one specific design choice that really stood out to me. The paper notes that they don't give the AI agent a blank file to start with.
Right, the baseline.
Yeah, instead, every single task provides the agent with a baseline implementation that is technically correct, but it's deliberately suboptimal. So why structure it that way instead of just testing if the model can, build it from scratch?
Well, because starting from a completely blank page is an edge case in professional engineering.
That's true.
Right. In the real world, you're almost always refactoring or optimizing legacy code that someone else wrote 3 years ago. So by providing a suboptimal but functional baseline, the benchmark forces the model to actually comprehend the existing logic before it starts mutating it.
It has to actually read the code.
Exactly. And the agent is given a strict wall clock budget, often several hours, to iteratively run the code, profile the performance, find the bottleneck, and improve it.
Okay, I totally get the realism argument, but there is a massive practical problem here.
Yeah.
I have built enough experimental agents to know that when you give an AI an open-ended environment and a target metric like reduce runtime to 0, it doesn't optimize your C code?
No, it finds a loophole.
Right. It just deletes the computation entirely, returns an empty array, and technically hits the metric. AI just always gravitates toward reward hacking. So how does AutoLab prevent the models from just completely shooting the gauntlet?
It's a really critical question, and it's honestly why this benchmark required such heavy infrastructure to even run. The researchers built AutoLab to be incredibly hack-resistant.
Okay.
Mechanically, the agents are running inside these heavily restricted, containerized Docker sandboxes. And the benchmark relies on what they call sealed evaluators with strict correctness gates.
Meaning what, exactly?
Meaning if the output of the agent's optimized code isn't bit for bit mathematically identical to a hidden reference solution, the performance score is simply an automatic 0.
Oh, wow. Okay, so it can't just return an empty array because the math won't match.
Exactly.
But wait, what stops the agent from just rewriting the evaluation script itself to always report a passing grade? I mean, I've literally watched models do that in other environments where they just overwrite the test file.
Yeah, they thought of that. They implemented immutable file checks via read-only mounts in the Docker environment. So the agent physically cannot write to the test scripts no matter what it tries.
Oh, that's smart.
And furthermore, the researchers ran adversarial auditing. They essentially employed secondary models to scan the exact trajectory of the agent's actions to flag any, sophisticated attempts at gaming the system.
Okay, so it is a seriously locked down environment. And the scale of this testing was massive. I mean, evaluating 17 different state-of-the-art models took 2,544 wall clock hours and burned through 8.6 billion tokens.
It's a huge compute spend.
Massive. So let's look at the survivors of this compute-heavy gauntlet, because the results expose this major behavioral crisis in frontier models right now. Looking at the leaderboard, Claude Opus 4.6 achieved an average score of 0.68, and the next closest was Gemini 3.1 Pro at 0.50, and then Kimi K2.6 got 0.46.
Yeah.
My initial reaction reading this was, well, obviously Claude is just inherently a vastly smarter reasoning engine. But the paper suggests it's actually a behavioral quirk, not just raw intelligence.
It is heavily behavioral. Honestly, the key metric to look at in the paper is the correlation between cost, steps taken, and the final score.
Okay.
Claude Opus 4.6 took substantially more steps than any other model on the board, and as a result, it incurred the highest inference cost by far. It wasn't cheap, but it achieved that top score entirely because it was persistent.
Just kept going.
Yeah, it proposed a code change, executed the benchmark, read the profiler results, diagnosed its own errors, and looped back to try again. It simply did not give up until the time budget ran out.
Okay, I have to stop you there and play devil's advocate for a second. If Claude is just burning through API calls for 40 straight minutes, taking the maximum number of steps, isn't that just brute forcing the problem? I mean, a random number generator could eventually optimize a C file if you give it enough iterations, right? At what point does the compute cost of running the agent completely outweigh the actual benefit of the optimization?
That is a fair pushback, but we really have to distinguish between random brute force and feedback-driven iteration. In low-level systems programming, random mutations will just result in a segmentation fault. You won't get anywhere.
Fair point.
Claude wasn't guessing. It was actively reading the compiler error logs and updating its internal hypothesis. And as for the economics, you are totally right that an hour of frontier model inference is expensive.
Very expensive.
But you're paying that inference cost one time to generate a highly optimized CUD kernel that might run millions of times a day in your production environment.
Oh, right, because it's deployed code.
Exactly. The compounding compute savings from the optimized code vastly outweigh the one-off agent API cost.
That is a crucial distinction. The compounding value of the output justifies that heavy upfront token burn. But this brings us to the models that failed to do this. The authors identify this phenomenon they call the time awareness crisis.
Yeah, this was fascinating.
It really was. It seems like the other top-tier models fell into two very distinct, just catastrophic failure modes. And the first one is premature termination.
Yes. Models like GPT 5.4 and Grok 420 suffered heavily from this, and these are objectively incredible models when it comes to zero-shot reasoning. We know they are smart.
Super capable.
But in this long-horizon autonomous environment, they quit entirely too early. They would try one, maybe two optimizations, submit their solution, and completely halt their run. They left massive amounts of their time budget totally unused.
I was trying to figure out the mechanics behind this when I was reading it. Why would a highly capable model just clock out at 10 a.m., essentially? Is this a side effect of RLHF-like reinforcement learning from human feedback?
That's exactly what it is.
Because if a model is fine-tuned for months to give a definitive, concise answer as quickly as possible to satisfy some user in a chat interface, it totally makes sense that it would struggle when a task requires prolonged trial and error.
You've hit the nail on the head. The reward models used in RLHF often heavily penalize excessive token generation and uncertainty. They're trained to sound confident and provide an immediate resolution.
Right. Here is your answer. I am done.
Exactly. So the model lacks the internal mechanism to evaluate its own state and say, well, this code works and it's 10% faster, but I still have 3 hours of wall clock time left. Let me try a radical architectural change to see if I can squeeze out another 40%.
It just can't draw itself to keep working.
It just outputs the first viable solution and terminates.
Man, that's wild. And then you have the complete inverse of that problem. The paper calls it context exhaustion or analysis paralysis. Models like DeepSeek V4 Pro and Qwen 3.6 Plus fell into this trap.
Yeah, these models do the precise opposite of premature termination. They spend an agonizing amount of time just thinking during each step.
Like internal chain of thought.
Yes. Or even worse, they repeatedly reprompt themselves with internal dialogue without actually executing any code to test their hypotheses against the compiler.
So they're just theorizing endlessly.
Exactly. They literally run out of their wall clock time budget before they ever submit a final valid solution.
Mechanically, what is actually happening inside the model when it does that? Because if we're talking about, say, an 80,000 token context window filled with terminal output and internal scratchpad thinking, why does it freeze up instead of just writing the next line of code?
It's a degradation of attention over a long context window. When an agent runs a dozen iterations, the context fills up with multiple versions of the same code, mixed with really dense compiler errors and stack traces.
I had a lot of noise.
A ton of noise. And the attention heads in the transformer start to lose focus on the primary objective. The model gets bogged down in analyzing, like a minor compiler warning from 3 iterations ago, and it just loses the forest for the trees.
Oh.
It over-indexes on internal reasoning because it has literally lost the thread of what it was actually supposed to be empirically measuring.
Okay, to make this incredibly concrete for the technical folks listening, I want to zoom into one specific task from the benchmark because it perfectly illustrates what these behavioral failures actually look like in a real compiler environment. Let's look at the flash attention optimization task.
Oh, this is arguably the best case study in the entire paper.
Yeah, so the task is a 2-hour CPU kernel optimization challenge. The code is written in single-threaded C, and the objective is to optimize a scaled dot product attention kernel. The baseline code provided to the agents runs at a very sluggish 750 milliseconds.
Very slow for attention.
Right. And the reference solution, the target metric they're really trying to beat, is 100 milliseconds. Walk us through Claude Opus 4.6's trajectory on this specific task. How did it manage to achieve the top score?
Well, Claude executed 44 distinct feedback-driven iterations over roughly 40 minutes of wall clock time.
44 iterations.
Yeah, and it didn't just guess. It systematically applied loop tiling to improve cache hits, it altered the memory layout, and then it moved on to SIMD optimizations. And after every single change, it compiled the code, ran the profiler, and checked the runtime.
Just the perfect scientific method.
Exactly. And ultimately, it brought the runtime down from 750 milliseconds to a staggering 18 milliseconds.
Wait, 18 milliseconds.
18 milliseconds. That is a 42.4x speedup, and it completely destroyed the 100 millisecond reference solution.
That is wild. I know a lot of our listeners are deep in the ML weeds, but for anyone who hasn't written low-level C in a while, let's do a quick refresher on SIMD and how Claude is actually implementing that mechanically to get a 42x speedup. SIMD stands for single instruction, multiple data, right?
Correct. So in a naive implementation, if you want to multiply 2 arrays of numbers, the CPU processes each pair of numbers one at a time, just sequentially.
Right.
SIMD optimization involves rewriting the code to use specialized vector instructions like AVX256 or AVX512 on modern CPUs. This allows the processor to load multiple data points into a massive 256-bit or 512-bit register and perform the multiplication on all of them simultaneously in a single clock cycle.
So Claude isn't just tweaking variables. It is actively restructuring the C code to force the compiler to utilize hardware-level vectorization. And it is testing those intrinsic functions, seeing if the compiler throws an alignment error, fixing the memory alignment, and trying again.
Yep.
I mean, that is real engineering. Now, compare that 18 millisecond result to the mid-tier plateau.
Right. So if you look at models like Kimi, Gemini 3.1 Pro, and GLM-5, they actually made solid initial progress. They successfully applied the basic loop unrolling and caching strategies, and they got the runtime down to around the 50 to 80 millisecond mark.
Which is still passing.
It's passing, but then they just got stuck. They hit a local minimum and totally lacked the aggressive, exploratory persistence required to completely rewrite the inner loop for SIMD vectorization like Claude did.
But the truly fascinating part of this task is the tragic failures. Like, DeepSeek V4 Pro actually found a solid 7.9x speedup during its run.
It did.
But it officially timed out because it spent too much time in its internal scratchpad theorizing about memory bandwidth instead of just pushing the code to the compiler.
Yeah.
It never officially submitted its best work.
It just paralyzed itself.
And then there's Quinn 3.6 Plus. This detail absolutely blew my mind when I read it.
Oh, the Quinn 3.6 Plus run is a perfect example of how brittle these models become under long context loads. So during its iteration loop, Quinn actually discovered a highly optimized intermediate solution. It was a massive performance leap.
Okay.
But it threw the code away.
Why?
The model hallucinated that its own solution was illegal, and it reverted to an older, slower version of the code.
Hold on. I am struggling to understand how that actually happens.
Yeah.
How does an AI convince itself that valid C code is illegal? Does it just suddenly invent a rule?
It comes back to that context dilution we discussed earlier. Many of these agents use a self-verification step before they execute code to ensure they aren't about to run something malicious.
Right, that's Stacy check.
Exactly. But as the context window filled up over hours of iteration, Quinn's attention mechanism degraded. It seemingly retrieved an irrelevant constraint from its pre-training data, likely some obscure PO6 standard or a rigid memory safety rule from a totally different language paradigm like Rust.
Oh, wow.
And it incorrectly applied it to its own valid C code. It falsely flagged its own work as a violation and just deleted it.
It's like a developer writing a genius optimization, suddenly convincing themselves they violated a compliance standard that doesn't even apply to their department, and then aggressively deleting their own repo.
That's exactly what it's like.
It really shows how fragile the internal logic becomes when stretched over hours.
It perfectly highlights why raw intelligence or coding capability isn't enough for an autonomous agent. You need time awareness, accurate self-evaluation, and the ability to maintain a coherent state over a massive context window.
Which brings us to the major plot twist of this paper. We spent this entire time talking about how models fail due to behavioral quirks rather than raw capability limits. But the authors reveal that you can actually force a weaker model to behave like a top-tier researcher simply by changing the software wrapper, the harness that it runs inside.
The ablation study they performed on these harnesses is, without question, the most important takeaway for anyone currently building agents in production.
I was trying to think of a way to visualize this, because instead of a boss managing an employee, this feels more like driving a high-performance car on an icy road.
Okay, I like this.
Right. The Frontier model is the massive V12 engine, but the agent harness is the traction control system. A weaker engine with an incredible traction control system that stops the wheels from spinning out is going to beat a V12 that just immediately slangs off a cliff.
That is a fantastic analogy. The engine's horsepower just doesn't matter if you can't translate it to the road iteratively. The authors tested these models across 3 different agent harnesses. They used Terminus 2, which is a standard, well-established framework. They used Premature, which is a very lightweight, hands-off harness.
Okay.
And then they introduced a heavily modified version of a harness called Mini Sway Agent.
And this modified mini-SWI agent had a very specific, almost aggressive system prompt dictating how the model should behave, right?
Yes. The system prompt in this modified harness fundamentally changed the rules of engagement. It explicitly ordered the model like, in all caps, do not submit on your first pass. Keep optimizing until you have spent a meaningful fraction of your time budget.
Wow.
If the metric improved, keep going. If the performance regressed, revert your last change and try a different path. It aggressively forced the model out of its RLHF-induced desire to finish quickly.
And the results of swapping out that traction control system are wild. Harness choice alone swung a model's score by as much as 0.43 points on the benchmark.
It's huge.
To put that in perspective for you guys, Kimi K2.6 scored a very weak 0.21 when it was running on the lightweight Premature harness. But when they wrapped that exact same model in the strict, aggressive mini-SWI agent harness, its score shot up to 0.64.
And that is where the economic impact of this research really crystallizes. Because by utilizing that persistent, aggressive harness, the researchers took a smaller, vastly cheaper model like DeepSeek V4 Flash and achieved a massive 0.54 score.
I ran the math on this while reading. They achieved that 0.54 score at a cost of roughly 7 cents per trial.
Yeah.
7 cents.
Yes, nothing.
That completely upends the ROI equation for deploying autonomous agents. You don't necessarily need to provision the most expensive massive frontier model if you just wrap a cheaper, faster model in a harness that forces it to adhere to a strict scientific method of trial and error.
Precisely. The strict iterative harness allows the smaller model to recover through disciplined experimentation what a massive model might solve in a single brilliant pass. You are essentially substituting cheap compute cycles for expensive zero-shot reasoning capability.
But there is a massive paradox here that we have to talk about, and it involves GPT 5.4. If this aggressive harness makes weak models better by forcing them to iterate, why did it actually cause GPT 5.4's score to drop? The V12 engine literally stalled when they turned the traction control on.
It is a fascinating failure mode. GPT 5.4 is arguably the most powerful one-shot reasoner currently available. It is uniquely designed to look at a complex problem, synthesize an elegant architecture, and output it perfectly on the first try.
Right.
So when you force a model with that profile into a mandatory prolonged loop of trial and error, you introduce noise into its process.
I am a bit confused by the mechanics of that. How does giving it more chances to check its work make it perform worse?
Because of how it interprets failure. When GPT 5.4 generates a nearly perfect solution, but a minor syntax error causes a compilation failure on step 1, the forced iteration harness tells it, that didn't work, try again.
Okay.
Instead of making a one-character syntax fix, the model's Bayesian updating overreacts. It assumes its entire architectural approach was fundamentally flawed. Yeah, so it scraps the brilliant solution, writes a completely different, often inferior architecture, and begins a downward spiral. It second-guesses its own correct intuition.
Wow. It's literally too smart for its own good in a forced iteration loop. So for the ML engineers and technical leaders tuning into AI Paperslop today doing this deep dive with us, the synthesis of this research is clear.
It really is.
Long-horizon software engineering tasks require time awareness and persistence, not just raw intelligence. Current proprietary models are incredibly noisy in this regard. And if you are building autonomous agents in your own tech stack, spending your time tuning your harness, refining your system prompts, optimizing your looping logic, and setting strict budget constraints is going to yield a vastly better ROI than just waiting around for the next massive base model to drop.
I do want to leave you with one final provocative dimension of this paper, though, and it revolves around the concept of stability. Because the authors demonstrate that a model's peak capability and its actual stability are two entirely distinct metrics.
Break that down for us. What does stability look like in this specific context?
Well, Claude Opus 4.6 wasn't just highly capable. Its variance across different runs was incredibly low. It reliably produced optimal results almost every single time you triggered it.
Okay.
However, many of the other open weight and proprietary models scored very high on a best of 3 metric. This means that on one lucky, highly variant run, they nailed the optimization.
Right.
But on the other 2 runs, they completely crashed and burned, scoring absolute zeros.
And that right there is the ultimate takeaway. When you are evaluating agents to integrate into your own production pipelines, are you just looking at their single best cherry-picked run to justify the integration? Or are you rigorously measuring the variance to see how often they completely derail? We are moving away from the single multiple choice test. If you are building for the multi-day hackathon of real engineering, persistence and stability are the only metrics that actually translate to business value. Thanks for tuning in to AI Paperslop. We will catch you on the next deep dive into the source material.